can be write as a mass volume. Variation in x or volume. The original length of that is a constant, which is related to the material itself. That is the variation in temperature. So you will see when the temperature changes and at times a constant will equals to a variation in the proportion of the variation in length and the original length. If the constant is known and it can be measured or tested by some measurements. If it is known and the variation in temperatures is known, the variation in the length or the value of the material is known. And that is the most easier variation of the thermal expansion. There is a zero of the thermodynamics that it can be expressed by this example. The exchange of energy between two objects because of difference in the temperatures is called heat. Consider two objects A and B that are not in thermal contact with each other, and a third object C that acts as a thermometer A device measuring the temperature of an object. First of all, we put the thermometer on A. Therefore, in this situation, the temperature of the A and the detector of the thermometer and the temperature of the detector of the thermometer will equal to each other. And as shown here, 22.5, which means the temperature of the object A and the temperature of the detector of the thermometer both equal to 22.5. Then we measure the object B, 22.5. In this case, the temperature of all the three parts, the first one, A object, the second one, the B object, and the third one, the detector of the thermometer, A, B, and C. If C equals to A and B equals to C, which means A will equals to B. That it looks easy, but that is a very important definition in thermodynamics. That is named by the Thirl's law of thermodynamics. If objects A and B are separated in thermal equilibrium, how do we read this word? Equilibrium. With the third object C, then A and B are in thermal equilibrium with each other. Here shows the question. Two objects with different size, masses, and temperatures are placed in thermal contact. Choose the best answer. Energy travels. A from the larger object to the smaller object, or from the object with more mass to the one with less mass, or from the object at a higher temperature to the object at a lower temperature. Number A, B, or C? C, of course. There is a definition of zero centigrade and 100 centigrade. After this picture, you are going to know how we define the centigrade. One common thermometer in everyday use consists of a mass of a liquid used mercury or alcohol that expands into a glass capillary tube when its temperature rises. Once we have marked the end of the liquid volume for our chosen environment on our thermometer, we need to define a scale of numbers associated with various temperatures. An example of such a scale is the Celsius temperature, formerly called the centigrade scale. The definition of the 0 centigrade in the centigrade scale is the temperature of the mixture of ice and water, and the temperature and the 100 centigrade is defined as the water which is just beginning to evaporate, to be boiled. Then, once the ends of the liquid volume in the thermometer have been marked at those 2 points, 0 centigrade and 100 centigrade, the distance between marks is divided into 100 equal segments, each corresponding to a change in temperature of 1 degree Celsius, or we can call the change of 1 centigrade. Well, the first definition of the temperature is by the centigrade, and it is defined by from 0 centigrade to 100 centigrade. Does anyone have thought about common 0 means nothing? However, in a mixture of water and ice, the heat in this mixture equals to 0 or not? The heat in the mixture of water and ice equals to 0 or not? No. Can the temperature of the mixture of ice and water further decrease? Minus? Yes, of course. Minus 10 centigrade, minus 100 centigrade of the ice is possible. It's possible. So the temperature can further decrease, which means the heat can still lose from the mixture of water and ice. So even if it is 0 centigrade, the heat in the mixture of water and ice don't equals to 0. There's still some heat in it. So we are going to have a new definition. Second one. Okay. We define the real 0 of the heat of a material as 0 K, and which equals to minus 273.15 centigrade. What does this number mean? That is the coldest temperature in our universe. If a material is with a temperature of minus 273.15 centigrade, which means there is a real 0 of it. 0 heat in the material. So there's no lower temperature in our universe. That is the lowest, which means no heat at all. So a new definition of K, 0K equals to minus 273.15 centigrade. So you will see how we change the K from C. If a few 73 K equals to, what's the number of it? Equals to how much?
Go to 0.6, yeah.
Yeah. Centigrade. So, K equals to centigrade minus the K is called the Kelvin temperature, and the centigrade is called the Celsius temperature. Both of these two scale of temperature can be used. And sometimes the Kelvin temperature is called the absolute temperature, because the 0 Kelvin really means zero heat, zero heat. A room temperature is generally defined to be 25 centigrade. What is this in Kelvin temperature? How to calculate it? 25 centigrade. To change it into Kelvin temperature, just do addition of the 273.15, and the final result is 298.15 Kelvin. Okay.
Hi. There is also another unit of temperature, Fahrenheit.
Finally,
Fahrenheit. We use it here. Fahrenheit.
sorry, I don't understand what you mean by Fahrenheit. Oh, you mean another scale of temperature?
Yeah.
Oh, here, F1. Yes, that is another one. And there is the equation to translate the Fahrenheit into centigrade or Kelvin scale. However, that is not international unit. It is not included in the SI. Therefore, we usually use the centigrade or Kelvin temperature. There is some equation for it. As we defined, the heat, when we put a cold spoon into a cup of hot coffee, what's happening? The first one, the coffee cools down, and the second one, the spoon warms up, which means a translation of heat from the coffee into the spoon. The interaction that causes a temperature change is fundamentally the transfer of energy from one substance to another. Energy transport that takes place solely because of the temperature difference is called heat flow or heat transfer. The energy transferred in this way is called heat. So, heat belongs to the energy. It's one candle energy. Then another energy, there are so many others. For example, kinetic energy, potential energy. We can define a unit of quantity of heat based on temperature change of some specific materials. The calorie is defined as the amount of heat required to raise the temperature of 1 gram of water from 14.5 centigrade to 15.5 centigrade. The heat needed to heat it. And the kilocalorie equals to 1,000 calories is also used. A food value calories is actually kilocalories. calorie here is a kilocalorie, which means the heat or the energy included in the food. A corresponding unit of heat using Fahrenheit, as you said, degrees, and the British unit is the British thermal unit, or BTU. 1 BTU is the quantity of heat required to raise the temperature of 1 pound, which is near to the kilogram, however it's different from it, of water. 1 Fahrenheit from 63 Fahrenheit to 64 Fahrenheit. That is another definition. However, only always use the British. It is not included in the international unit. Of course, even though it is not international unit, it can be transported. And there is an equation of it. 1 calorie equals to 4.186 joule. The joule may be more familiar to us. In the last semester, we have learned the work and the kinetic energy. Remember, kinetic energy, all the work, and the final resulted work can be that is both a unit of energy, and a 1 Newton per meter equals to 1 joule. So, in the last semester, we have learned something about energy, and the most used is the kinetic energy or the potential energy. In this section, we are going to learn the energy caused by the temperature, and both energy, no matter it is kinetic energy or potential energy or the energy in heat, can be transformed. And there is a transformation or equation of the transformation of energy into one unit to another. The transformation of calorie to joule, of BTU to calorie and to joule. The calorie is not fundamental international unit. The International Committee of Weight and Measures recommends using the joule as the basic unit of energy in all forms, including heat. So we use the joules too. The definition of specific heat. If you remember, there is a definition of 1 calorie, the amount of heat required to raise the temperature of 1 gram of water from 24.5 into 25.5 centigrade. Does anyone have questions? Why water? Why from 24.5 to 25.5? How about iron? Gold? Or copper? Or stone? To increase its temperature from 1 to 2 centigrade. Why water? Why this ranges of temperature? Because the specific heat of materials will change as a function of the type of the material and change as a function of the range of the temperature. To increase the ion from temperature 1 centigrade to 2 centigrade, the heat need is less than the heat need to heat the water from 24.5 to 25.5 centigrade. Because there is a difference from them, and the difference is caused by the specific heat of it. In this equation, Q equals to mc delta T. The heat required for temperature change delta T of mass N, where C is the quantity. Q equals to M times C times delta T. Variation in temperature, mass of the material, and the specific heat of the material. For infinitesimal temperature, change dt and the corresponding quantity of heat dq. You have learned the integral? Part of it? Oh, good. In above equations, Q and delta T can be either positive or negative. A positive one means heat enters the body and its temperature increases. That is the most common situation. And there's another one when the specific heat is negative, which means, the positive means the heat, dq. When the dq is positive, which means there is an increase in heat and the temperature of the material increases. Or when the dq is negative, which means there is a leak of the heat and thus the temperature decreases. The specific heat of water is approximately 4,190 joule per kilogram and per Kelvin temperature, or 1 calorie per gram in centigrade, or 1 BTU per 1 B times is the specific heat of the material fixed as known here. Why it is defined as it increased from 24.5 to 25.5. Okay, if you know it, can you make sense of this? Is the specific heat of a material fixed? If it is fixed, should we define the temperature ranges here? If the specific heat is fixed, there is no need to definition of it. No matter it is increased from 1 centigrade to 2 centigrade, or from 24.5 centigrade to 25.5 centigrade. If a specific heat is fixed, that two situations equals to each other. Therefore, it is not. It is not. The specific heat of a material always depends on somewhat on the initial temperature and the temperature interval. So the specific heat of the material varies with the temperature. Here shows the variation of the specific heat of water with temperature ranges from 0 to 100. For the minimum, it is almost about 4,108 joule per kilogram times Kelvin scale, Kelvin temperature. And the maximum is about 220. The problems and examples in this chapter we will usually ignore this small variation because you will see the variation of the specific heat is less than 100%. So even it is a variation one, we always treat it like an ordinary one. Okay, for example here. During a boat with a food, an 80 kilogram man ran a fever of 39 centigrade instead of the normal body temperature of 37 centigrade. Assume that the human body is mostly water. How much heat is required to raise its temperature by that amount? The most used equation 80 kilogram. 80 kilogram. However, there's a difference in temperature. Initial 37, internal 39 centigrade. What we are going to calculate is the heat needed to heat the body of 37 to 39. This problem uses the relationship among heat, mass, specific heat, and temperature change. In this equation, what we want to know is the heat. What is known? M, C, delta T. Which was known? The mass of the body is known, of course, 80 kilogram. The specific heat of the body. Since the human body is mostly water, so it is treated like the water. It's treated like water. And the specific heat of water we can know about here. From 37 at this point to 39. 4,180. So specific heat. Okay, it is shown here. The delta T variation in the temperature from 37 to 39 to centigrade. So all of those three parameters are known. So do the multiplication rate. The result turns out to be 6.5 times 10⁵ joule. Sometimes it's more convenient to describe a quantity of substance in terms of the number of moles rather than the mass of material. Recall from your study of chemistry that the mole of any pure substance always contains the same number of molecules. Does anyone still remember the mole? What's the number of the mole? I can check it for you. That is acknowledgement in chemistry course. The mole is always used to describe the number of atoms, science, the number of atoms is always a huge number. Therefore, the more is used. 1 more means 6.02 times 10, 23. 23. And the transport from the more weight to the weight of it. There's a definition of it. The more mass of any substance denoted by the large M is the mass per mole. The quantity, large M, is sometimes called molecular weight, but more mass is preferable. The quantity depends on the mass of a molecule, not its weight. For example, the more mass of water is 18 gram per mole, which means 1 mole of the water molecules. The weight of it is 18 gram, or 18 times 10 minus 3 kilogram, which is equal to each other. 1 mole of water has a mass of 18 gram, or 0.018 kilogram. The total mass of material is equal to the mass per mole times the number of moles n. Why we use moles is because it is mostly useful. It is not clear. Not so clear, but it is acceptable. 1 more of water. The water can be written as HO2, right? And the weight of 1 H is 1. The weight of the oxygen atom No, 8. 8. It is number 8, but the weight of it is 8 times 2.
Yeah.
So 2 plus 16 equals to 18. 18. Which means 1/4 of the water molecules will equals to 18 gram. And 1/4 is 602 times 1023 of water molecules equals to 18 gram. 18 gram. Why it is useful? Because if its consist is known, I still want to find a better picture. Yes,